Mechanical properties of solids. In this chapter, first we need to discuss about the stress. Stress is defined as the ratio of restoring force to the area, that is F by A. And stress units are SI units are Newton for meter square and CGS units are Dyne for centimeter square. Stress dimension formula is m L power minus 1 T power minus 2. After this, we need to discuss about the strain. Strain is defined as the ratio of change in dimension to the original dimension, that is delta L by L. Strain has no units and no dimensions because it's a ratio of same physical quantity. It's a ratio of same physical quantity. On stress and strain, by using the stress and strain, one important law is there, that's the Hooke's law. Hooke's law. According to Hooke's law, stress is directly proportional to strain. Stress is equal to proportional constant into strain, where proportional constant is called as the modulus of elasticity. Proportional constant is called as the modulus of elasticity. Generally, modulus of elasticity represents with capital E. So, stress is equal to capital E into strain. And modulus of elasticity is defined as the ratio of stress to the strain. Stress to the strain. That is, modulus of elasticity is equal to stress by strain. Its units are Newton for meter square and its dimensional formula is m L power minus 1 T power minus 2. Depends on kinds of deformation. Modulus of elasticity are three types, which are Young's modulus, bulk modulus and rigidity modulus. Young's modulus, bulk modulus and rigidity modulus. First we can define as Young's modulus. Young's modulus is defined as the ratio of longitudinal stress to the longitudinal strain. Young's modulus is defined as the ratio of longitudinal stress to the longitudinal strain, that is F by A by delta L by L. It means F by A into L by delta L. F by A mean and Y is equal to means Young's modulus is equal to F into L by A into delta L. F into L by A into delta L, and its SI units are Newton for meter square and CGS units are Dyne for centimeter square. Its dimension formula also same as that of modulus of elasticity, that is m L power minus 1 T power minus 2. Because of all modulus of elasticity is defined as stress by strain, but different stresses and different strains will come. Strain is a dimensionless quantity, so only stress dimensions and strains dimensions will be applicable for Young's modulus, bulk modulus and rigidity modulus. That's why Young's modulus units are Newton for meter square and dimension formula is m L power minus 1 T power minus 2. Young's modulus only applicable for solids. Young's modulus applicable only for solids. It's not applicable for the liquids and gases. On this, no number of applications are there. On Young's modulus, number of applications are there. We can concentrate on applications on another video. Okay. Before that, we can discuss bulk modulus. Bulk modulus depends on the bulk modulus defined as the ratio of volume stress to the volume strain. Bulk modulus defined as the ratio of volume stress to the volume strain. So, bulk modulus K is equal to F by A by minus delta V by V. Minus delta V by V. Here we are using minus because minus sign represents that final volume will be decreases. Final volume will be decreases. That's why we are using the negative sign. So, bulk modulus K is equal to F by A by minus delta V by V. We can write as F by A into minus V by delta V. F by A is nothing but a pressure. So, we can write as K is equal to minus delta P into V by delta V. Otherwise, K is equal to minus V into delta P by delta V. Generally, delta P increase in pressure, but delta V decrease in volume, and capital V is the original volume. That is the bulk modulus. Bulk modulus applicable for all states of matter like solids, liquids and gases. It will be applicable all states of matter. Generally, bulk modulus more for solids and less for gases. Hence, we can give the order like bulk modulus of solids is greater than bulk modulus of liquids is greater than bulk modulus of gases. It's important one. Bulk modulus of solids, bulk modulus of liquids, bulk modulus of gases. Next, rigidity modulus. Rigidity modulus defined as the ratio of shear stress by shear strain, shearing stress by shearing strain. Eta is equal to shear stress F by A. Shear strain represents with the theta. So, eta is equal to F by A by theta. Eta is equal to F by A theta. Rigidity modulus SI units are Newton per meter square, and the dimension formula also same, m L power minus 1 T power minus 2. Rigidity modulus applicable only for solids. Rigidity modulus applicable only for solids. In this case, shape of a body changes, but its volume remains unchanged. In the case of rigidity modulus, the shape of the body only changed. Its volume remains constant. After this, we can discuss about the compressibility. Compressibility means the reciprocal of bulk modulus. The reciprocal of bulk modulus is called as compressibility. Compressibility is equal to 1 by bulk modulus, that's nothing but minus 1 by V into delta V by delta P. Here it is, compressibility units are meter square for Newton. Compressibility units are meter square for Newton. Rigid body compressibility is 0. Generally, rigid body compressibility is 0. And ideal liquids, if you take any ideal liquid, that ideal liquid compressibility also 0. Ideal liquid compressibility also a 0. Remaining materials, any solids or liquids or gases have some compressibility. Next, after this, Poisson's ratio. Poisson's ratio defined as the ratio of lateral strain to the longitudinal strain. Lateral strain to the longitudinal strain, that is sigma is equal to minus delta R by R whole by delta L by L, that is delta R by R into L by delta L. Here also we need to use negative sign because radius of the rod will be decreases, so we can use negative sign for the Poisson's ratio. Here lateral strain by longitudinal strain means lateral strain is nothing but the ratio of change in radius to the original radius is called as the lateral strain, and longitudinal strain means the ratio of change in length to the original length is called the longitudinal strain. This is the lateral strain and longitudinal strain. Generally, Poisson's ratio has no units and no dimensions because of it is also a ratio of same type of physical quantities. That's why no units and no dimensions. The theoretical values of Poisson's ratio are -1 to 0.5. And the practical limits of Poisson's ratio is 0 to 0.5. For solids, Poisson's ratio value is